Okay, so the hyperbola, remember, is just another one of the slices off a cone, right? So the slice that you're doing is a vertical slice. Maybe I could redraw that double napped cone for you. Remember the game where we were slicing the cone? Double napped cone ninja? And there was one slice that we got to sort of at the end of our discussion where you slice straight down like this. And when you slice like that, it creates two cross sections, one for each nap. And you get these two U-shaped thingies, which really are not parabolas. They're actually following the edges of the nap. They're actually quite straight. But that blue, if you're looking at it perpendicular to the cross section, it looks more like this. There's two pieces for sure. And these end points are more straight than a parabola would be. In fact, there are guidelines. These are the actual edges of the nap here. Okay? Can't really draw it very well. But the actual edges of the nap of the cone guide those slices up to infinity, and they form more straight-like shapes. There is curvature, but it's towards the vertex areas, you know, and then they kind of straighten out. Okay, so that's kind of what it looks like. If you wanted to construct this set of points using a game, the game might look something like this. Draw any two random points on a piece of paper, pick a number, let's say 12, and then start dreaming up values that differ to make 12. For example, 13 and 1 have a difference of 12, right? What's 13 minus 1? 12, right? 14 and 2 have a difference of 12, right? 15 and 3 have a difference of 12. 98 and 86 have a difference of 12, you see. And so the game becomes, can you find points on the plane that are, 13 inches from one black dot and 1 inch from the other? So that's the game. I'll do my first point here. We'll call it A. How about right here? It's 1 inch from the first black dot, or the right black dot, and 13 inches, from the left black dot. So I successfully found 1 point. I can actually think of 4 points, though, that obey just this first rule for A. So A could be here, A could be here, A could be here, A could be here. In all 4 of these cases, point A is 1 inch from one black dot and 13 inches from the other. So you kind of get a 4-for-1 deal. You get 2 lines of symmetry on an ellipse. Next, you might try 14 and 2. So I can do that as point B, you see. And to do that, you're going to need to make sure that your points are actually a little further from both of the black dots. It's not 13 and 1, it's 14 and 2, both numbers bigger than before. So you're going to get a point actually maybe here for point B, or here, or maybe here, and here. So you obviously don't have to draw this. It's just a game. I'm trying to show you how the game works. In this game, I'll say it one more time, the only rule is the point, the blue point, for example, B, has to be a certain distance from one black dot and a certain distance from the other black dot, and the difference has to be 12. So whatever this segment is and this segment, they differ to make 12. I'm trying to do like 14 and 2. But you can see how this actually would lead us to things like 98 and 86, you see. Points that are extremely far away from the center, right? In fact, we actually would never be able to construct points right in the middle, because the problem with points in the middle here is if you have like a point right at the dead center, it's equidistant from the black dots, and the difference in those two lengths is actually 0. That's not what we want. We want the length difference to be 12. See? So as you play this game, and if you actually did this with a ruler, it takes a long time, you could actually construct something like this. This is kind of what it would look like when you're done. The black points would not actually be part of the curve set. You can see my point A here is in the wrong spot. And I mean, you would have to use a measuring tool to really get it right. But your points would follow these green paths. Obviously, I'm a horrible artist. But you would get a hyperbola. Why? Because that's the game. That's the game.
What about the green points that are between the two?
Yeah, there are a couple of green points that fall between the two black dots. But this point, for example, is maybe 12.1 units from this, and only 0.1 units from here. So this distance, let's say this green dot right here, from here to here might be 12.1, and this might be 0.1. So the difference is still 12.
Black dots were 12 apart.
No, I didn't say that.
Oh, okay.
I never said that.
So you could technically.
Although the vertices are 12 apart. Okay, so the game is a little different. The game is very hard to play, and most people probably wouldn't play this game. It's not the kind of game you play. But you can see how a game could produce a strange shape, and that shape could have a name. What's interesting to me is that it's the same as the slicing of the conic, the slicing of the cone. That's interesting that those are one and the same. So let's look now at just some of the symbols and the measurements and what we call things. So first of all, when you draw a hyperbola, you do kind of need these lines, because these lines are not exactly optional. They really are the guidelines. They are the cone, you see. They are the edges of that cone. So they also help us to draw the branches carefully, to make them look like they're going the right directions. Now the two purple lines are not part of the hyperbola, but they are guidelines for the hyperbola. Also, they do not necessarily have slopes +1 and -1, although they do have opposite slopes. They also are not always perpendicular, although that could happen. Okay, so let's just measure some things. Fortunately, we still call this distance A, and we still call this the center, and we still call this the vertex. So that's good news. We haven't changed the name center and vertex, and we haven't changed the distance between them, and that's still called A. Good news. The point that's inside here, that's actually the two green points are the points that sort of started off the whole game. Those, you might guess, are the foci. So there's a focus on the left and a focus on the right, one on each side. And fortunately, the distance from the center to the focus hasn't changed. That's still called C. Good news. One thing has changed, though. You'll notice that C is now longer than A, whereas before, remember, A was the biggest possible of the three ABC. Now it's A that's top dog on the hyperbola.
C, you mean C?
I meant to say C, yes. A is top dog on the ellipse. C is top dog on the hyperbola. Okay? Thank you. So, where is B? Well, I like to think of B is for box. Okay? B is for box. Many of you remember drawing a box for this sort of thing. Here's how you're supposed to construct the box. The box should be wide enough to touch both vertices. And the box should look like its diagonals pass through the center. So in other words, it needs to be a rectangle. And it needs to look like the asymptotes are the diagonals. You see? So this is not just a random box. This is a very, very specific rectangle whose endpoints are the vertices and whose diagonals are the asymptotes. Now it's obvious where B is. B is the center to the top of the box. The distance from the center to the top of the box. So I have to erase a little here and there. Hopefully you don't have to, but this is B. So sometimes people ask me, what's B? I say, well, it's the box. They're like, what do you mean? Well, it helps me draw my box. Or if the box is already there, I measure half of its height, and that's my B. Notice that this box is actually 2A in its width and 2B in its height. Okay? So it's not an A by B box, it's a 2A by 2B box, technically. Another thing I sometimes will say, if someone asks me, what is B? I'll say it is the rise for that purple line. It helps me get the slope of the purple line right. See, the slope of this purple line is B over A. See, it rises by B and it runs by A. So the purple line has slope B over A. Let's go ahead and include that in our drawing. This asymptote has equation y minus y1 equals m times x minus x1, like any other line. But the slope is clearly B over A. So I'm not going to put m there. I'm going to put b over a. And this line over here is y minus y1 equals negative b over a times x minus x1. What is x1 and y1 in the point slope form of a line? What is that x1 and y1 in a line? You guys know what that is? Some of you are so used to using y equals mx plus b, it's crippled you. You should have replaced y equals mx plus b with this a long time ago. What is x1 and y1? Any point the line contains. Can you tell me one point we know for sure this line, both lines, contain? The center, correct. So these two, x1 and y1, are h and k. Because these lines pass through the center, for sure. Okay, so this is just sort of a erase it and put in the best answer kind of thing. I think we should put h and k right there. Same thing with the other one. And now we're ready for an example. Oh, one more thing. You'll notice right in the center, let's pick a color. Let's go with this, like puke green. Right in the center is an ellipse. See it? An ellipse whose equation is x minus h squared over a squared plus y minus k squared over b squared equals 1. See that ellipse there in the center? You know what the equation of the hyperbola is? X minus h squared over a squared minus y minus k squared over b squared. Everything's color-coded here. The brown, the like disgusting brown color there, is the equation of that ellipse, and the red is the equation of the red hyperbola there. Notice they're exactly the same except for one thing. What's the difference?
Minus.
The minus. Correct. All right. Now what would happen if everything was sort of on its side and the branches of the hyperbola were like one pointing up and one pointing down? What would we do with that orientation situation? Okay? Yeah, so here's the rule with hyperbolas. Please listen very, very carefully. In the world of ellipses, you always adjust your denominators so that the bigger one is underneath the term that represents the shape. For example, if it's a wide one, we put the bigger number under the x. Remember that? And when it's a tall one, we put the bigger numbers under the y. It doesn't work that way with ellipses. You do not have a choice where to put a squared. It always goes under the first fraction. A squared always goes under the first fraction. Which means if this orientation is tilted, you've got to switch something. You're going to actually be switching the numerators around. Okay? So we'll draw one more picture on the next slide, just so you have the formulas for the vertical case. If your graph looks like this, box, lines, branch, branch. Okay? If this is the situation, you would actually use y minus k squared over a squared minus x minus h squared over b squared equals 1. I had to switch the tops around because I'm not allowed to change the bottoms on the hyperbola. A squared is always first, and it's not always bigger. A squared not always larger. Okay, let's try an example. You know, one with that actually has numbers in it. Oh, by the way, the equation of the asymptotes here, the only thing that happens is you switch the h minus k, x minus h and y minus k around. So the equation of these asymptotes would be y minus k equals a over b, x minus h. This is the consequence of switching x and y around. And this one would be y minus k equals negative a over b, x minus h. But let's try an example. Can I move on to the next slide? Okay. If you really hate my messy drawings, you can look at the book for beautiful artwork. I spent all my good artwork on Mr. Ellipse over there. So I'm all burned down on good artwork. Okay, let's see here. We're going to try to Find the standard form of the equation of the hyperbola with center at I want to do, I think it's 5, -5. Let me just double check that. Give me 1 second. No, center at 1, -5. I want one vertex at -5, -5. And one focus at 11, -5. Okay, so let's see here. I modeled this exactly after my example 1 for ellipses. So, you can actually treat this like an ellipse problem, and when you're done with it, change the sign in the middle to a negative. You can do that. You just have to make sure that your a squared is actually under your first fraction. All right, let's take a look. Let's draw a sketch. That's kind of what we did the first time we did a problem like this, a couple days ago. So 1, -5. This is my center. We'll use capital C for center. 11, or sorry, -5, -5. This is my vertex. One of them anyway. There's actually 2 vertices, remember? And 11, -5 for one focus. Okay, now I thought that a hyperbola was supposed to have 2 vertices and 2 foci. So go ahead and find the 2 missing points. There's one more V point and there's one more F point. Go ahead and find those. I'll pause my recording. Okay. Did you find the missing focus yet? Or are you you're still plotting?
Yeah.
Okay. Fair enough. Anyone find the missing vertex yet? Looks like I didn't leave quite enough time. What'd you get, Jack?
7.
Yeah, you're right. It's at 7, -5. How would you justify that?
Because A is 6.
Yeah, there's symmetry, right? So he's right. A is 6. You can tell because this distance is 6. So you would have to go, because it's from 1 to -5. If you go from 1 to -5, that's a total of 6 spaces. So if you want to find the other one, you're going to have to go 6 to the right, but you're starting with 1. So it's going to be basically 1 plus 6. You got the other focus? Okay, so where's our other focus?
-9,
-9, -5? Yes, you're right. The other focus is back here. Why is that?
The distance from vertex to focus is, or I just did each vertex to each point of focus is the same, so.
Yeah. You can see that
I said that wrong.
from, I know it's hard to say, but if you go from C to F, in either direction it should be the same. So if you're going from 1 to 11, that's a total of how many spaces? 10. You're using subtraction, I would assume. So it's 10 spaces to go this way. So you go 10 spaces backwards from 1. So 1 minus 10 is -9. So that's where your other focus is at. In fact, you could actually draw an ellipse, but the foci are outside it right now. We're going to draw the hyperbola, remember? That's our goal today. So the hyperbola actually sprouts out of the vertices. So there's one branch, and here's the other. Okay, so I really gave you 2 distances on a silver platter. One of them was A. This distance is A. It's clear that A is 6 from this problem. The other distance I gave you was C. C was 10. It was given all along, you see. So what about B? B is important. Well, B is for box, right? So how are you going to find B? That's what this equation is for. Today it's a squared plus b squared equals c squared. This is your universal relationship between a, b, and c. C is now the longest of the three, a, b, and c. So let's go ahead and plug in c and a. We have 36 plus what is 100, and that would be 64. Or you could say b is 8. Well, b is for box. We've been counting sideways for a while. Now we're going to start counting up and down 8. Okay, so starting here, going up 8 spaces, puts me up here at positive 3. So this purple point, I'll put a little star up there, that is the top of the box. And if we go down 8, put a little star there, that's the bottom of the box. And the box ranges from negative 13, all the way up to positive 3. And its domain, the box's domain, is vertex to vertex. So if you could draw a decent looking box, you can finish this sketch. You just need the diagonals. Notice that the diagonals, you should not be trying really hard to make them pass through the origin. Okay? That's not the goal. The diagonals of the box should pass through the center. In fact, we don't even use the origin on these problems. Every counting exercise is done right from the center. Every now and then I have a student who counts everything from 0, 0. This is everything. Start at the center, that's your origin. Okay? Start at the center, count A, B, and C. There's your graph. And you can make your red curve sort of follow the green dashed lines. But what's the equation? That's what we were asked for, right? Okay, so it should be as simple as doing kind of an ellipse equation with a minus in between. The center was at 1, negative 5, so we're definitely going to have a x minus 1 squared and a y plus 5. It's a minus in the middle because it's an ellipse. There's still an equal 1 on the right. And how do you decide what you're going to put underneath? You don't have a choice. A always goes first. You don't have a choice. Now how did I know to put x first? Well, this one is sideways. This hyperbola opens left and right, so x is first. And A is always first. Now Matt showed me that on his calculator he has a program for conics. He can actually type in A, B, H, and K, and it'll graph hyperbolas and ellipses and all that. Now with the hyperbola program that he has, there's two programs. One for this style and one for this type that's standing up, like this. But on the ellipse style, on the ellipse program, there was only one program. Why didn't they write a second program to help you graph vertical ellipses?
I think it's because they assume which one, like whichever side's smaller, it'll be able to graph that way. Whichever the bottom is smaller.
Yeah, addition is commutative, right? So if this were a plus sign, you would just leave it to the user to put the bigger number in the right spot for the ellipse. But since subtraction is not commutative and you're not allowed to reverse it, they had to have two separate programs to get you to graph it properly. You see? So you have to situate A and B. Matt and I were talking about that yesterday. That's a cool discovery there. So you have two questions. Don't be surprised if you have to complete the square, right? Complete the square, get it looking like standard form. Worksheet's on the printer if you need it. Two problems. Graph paper, please. Who needs graph paper? I'll print it for you right now. I sure can give you graph paper.
When you post the thing online,
There's your graph paper. Just print it.
I want to see the first one.
What?
That